came up during discussion, and more people could be confused about that. So I want to spend a little bit of time on that. As to how is it that you have these momentum eigenstates, which are good eigenstates in relativity, but position eigenstates do not come. So let me do this in a slightly different way, which will illustrate the point. See, what we are after is this particular propagator, x2, x1, where these are four-dimensional events in this space. This is what we wanted, even in the case of non-relativistic theory. And we said that in the non-relativistic theory, so this is non-relativistic point mechanics, we demonstrated that this could be written as x1. Now this is vectorial, p is equal to 0 eigenstate of the position operator, e to the minus it, the Hamiltonian, which was just p square by 2m. This should be h2. This is h1. Okay, we showed this. And while showing this, we introduced a complete set of momentum eigenstates here, and then integrated it out and explicitly demonstrated it. And this needed introducing the momentum eigenstate with the following properties. The first is that integral over d3p, in our convention with the 2 pi to the power 3 here, p is 1. This is the completeness condition. Then we also had the condition that x p. Okay, the way we argued for this is, let me remind you, if you take a state and you take its coordinate basis, this is how it will look. And if I look at the same state with momentum basis, I will have a psi p with a px here, summed over all p. And in our convention, this is the momentum space wave function, this is the coordinate state wave function, and this is e to the ip dot x. Okay. So I would have written down here e to the ip dot x. With these two properties, from this we would have done the non-relativistic propagator property. Now what goes wrong when we do the relativistic propagator? So let us look at that a little bit more closely. So if you try to do the same thing for relativistic propagator, the main trouble comes from Lorentz invariance, and this probably was not clearly emphasized yesterday, so let me go through that. So what we are trying to do is to see whether the relativistic case, you can write it like x2 e to the minus ith x1. Now if we succeed in this, it would be wonderful, it's Nobel Prize, because we would have got a single particle Lorentz invariant relativistic description with some Hamiltonian. I am not even saying what is Hamiltonian should be. If you can write this, we know what the left hand side is. If we can write this for any operator h, then we are through. But what will happen is that it will not work, it will conflict with Lorentz invariance. So let us try to go through the same steps which we did here. What we will do is to introduce the set of complete momentum eigenstates, and I want to write an integral over d3p over 2 pi the whole cube. But we want the momentum space integrations to be Lorentz invariant, so I have to put this 2 omega p. This is what causes half the trouble. You put this here. Then I have the x2 e to the minus it, some Hamiltonian, which depends only on momentum for a free particle, p x1. Up to this, everything goes just like in non-relativistic mechanics. Now, since h is only dependent on p, I can just simplify this. I put a P here, and I have a P x1 here, and I have a e to the minus I, whatever is the eigenvalue for the Hamiltonian as a function of momentum t. Okay, this is up to this point is smooth sailing. Now we want to know what this is. Just because of the commutation relation, we know that it should be proportional to this. But the eigenfunctions can be multiplied by some constant here. So if I do that, this expression here has to go into some constant, which I will come up with a mod square, Cp square, e to the Ip x2 minus x1, which I will call x. Okay. So instead of this, I have kept a constant Cp here. That mod square of that will appear here. Right? Here is the problem. We know that e to the minus I omega pt into e to the I p dot x is Lorentz invariant. So this factor plus this factor is Lorentz invariant. The integral d3p upon 2 omega p factor is also Lorentz invariant. And we want the final result to be Lorentz invariant. That means this mod Cp square at best has to be a Lorentz invariant scalar built from the 3 vector momentum v. Okay? There is no such scalar except a constant. Here is where Lorentz invariance comes from. For example, you could have said, well, let us not worry about it. Let me take this to be equal to 2 omega p. That is, you put a square root of 2 omega p. Then this will cancel with this. The old problems like localization etc. will go away. In other words, at t is equal to 0, I will get a Dirac-Delta function. But the expression for the propagation which you get will not be Lorentz invariant. So it is the Lorentz invariance combined with, in some sense, quantum mechanical principles like the uncertainty principle, which tells you that the particle cannot be localized. I mean, this we talked about even earlier when I said that because you are doing a special relativistically invariant theory, energy and mass can be converted to each other. So if there is a delta x uncertainty in the position which leads to 1 upon h cross upon delta x uncertainty in the momentum, when you lower the delta x to a value below something like h cross over mc, delta p will be larger than mc. That will violate your original postulate that you are working with a single particle Hamiltonian. Which is another way of saying this is, if you take x2 sandwich with t is equal to 0 here, this t will go away, and the only way you could have got a Lorentz invariant reaction is to keep this as some constant. I mean, the moment you can keep it as a constant, it's good to normalize it to 1. So then e to the ip dot x upon this 2 omega p is what is going to tell you that it is not a Dirac-Delta function. Okay? Fine. So in order to connect it up with things which you may read in other textbooks, let me just explain that part as well. What we do in standard textbooks is to look at the Hamiltonian for a relativistic particle as something like square root of p square plus m square. Now,
in the non-relativistic picture,
right.
We get to the second part, this one,
yes.
By invoking that the Hamiltonian is the generator of time translation.
That is one way of doing it.
Right. So, I mean, what's happening in the relativistic domain which is preventing it from happening?
No, it will work perfectly fine if you use the fully Lorentz invariant generator of the four-dimensional thing. I'm going to do that in a minute. But that will give you the Schumann's proper time description. Okay, I'm going to do that in a minute. And then the correspondence will be complete. But before I do that, I wanted to do the textbook example. In the textbook, you would have written this down. Then you would have said that this is going to be minus del square plus m square square root. And the whole question is, how are you going to implement the square root? The square root makes this a non-local operator. It can be defined only in Fourier space. Or you have to play the Dirac trick where we said that let the square root be some gamma mu d mu plus some constant, and And we are not going to deal with the spinorial representations right now, so we will not go into that. The easy way out is to square it. Instead of working with h psi equals e psi, you can try with h square psi is equal to e square psi. If you do that, you run into the same problem, the old problem which is described in the textbook, that there is a omega p and a minus omega p comes out as an eigenvalue. There are both positive unity solutions and negative unity solutions. Now, when we did it in this way, we said that in the relativistic context there is this question mark. What you actually get, we know what we get because we know that the x2, x1 is actually going to be obtained. Remember what its Fourier transform was? Spatial Fourier transform. When we did this,
Sir,
yeah. Heavy.
so why will the positive and negative energy solutions, why will they have
Okay. The reason they create problems, so to speak, is that you normally see particles with positive energy. You have never seen a particle with a minus omega p. In a purely free particle theory, you can choose boundary conditions in such a way that you stay completely within the positive energy domain. But the moment there are interaction, there is always a transition between this positive and negative energy state. And this is what Dirac avoided in the case of fermions by saying that all the negative energy states are filled. But the moment you say all the negative energy states are filled, you are not talking about single particle description anyway. You have an infinite particle description because you need infinite number of electrons to fill all these negative energy states and then one electron on top. Okay. Fine. So this we calculated and we found that this is given by 1 upon 2 omega p e to the minus I modulus of t. So let me write this as theta of t e to the minus I omega pt plus theta of minus t e to the I omega p t. Okay, so this is the Fourier transform. Spatial parts create no problem. So I could have put the spatial part on that side and I could have integrated. So that would have given me, if I remove this part out and I put the spatial part on the side, I get integral over d3t upon 2 pi the whole cube. And let me keep this 1 upon 2 omega p also here. And I get this e to the I p dot x. Now if you compare this with what we have got here, you will see something interesting. You could have got this part, the theta of t part, by this procedure. And you could have got this theta of minus t part if I have flipped the sign of h. Right? So you could have written this x2, x1 in a very funny sort of way as x2, x1 here could have come from x2 and you write here the same theta of t kind of structure which is equivalent to e to the minus, okay, let me write it in expanded form, e to the minus ht theta of t plus e to the iht theta of minus t x1. Okay, so we do have this formula. Now the whole question is, can this be written as e to the minus it times some operator rho? The answer is obviously no. Okay, you just look at both t positive and t negative and you see that it cannot. So there is no single Hamiltonian whose evolution will give you this. What you need is positive energy modes has to be propagated backwards and negative energy modes has to be propagated backward, that is, I mean, forward. That is exactly, probably I said it wrong. Negative energy has to be propagated backwards and positive energy has to be propagated forward. And that is exactly what this the propagator which we have computed from path integrity is telling us. Okay? So this is the basic point. If you combine Lorentz invariance plus this, there is no single particle description which can be obtained with an x2 and x1 here and a t here. In some sense it also makes sense. In this kind of a description you have separated time from space. And if you go around separating time from space in special relativity, something will give you. Okay, that is exactly what it is telling. There is also a closely related issue to this, which has to do with the fact that in non-relativistic mechanics you have two kinds of integrals. One is this integral over d3p. Forget 2 pi to the power 3 for a minute. We have to put 3 by 2 in order to make it symmetric. There is also this integration over d3x. Okay? And in non-relativistic theory, I could have used this completeness condition where I say pp on this and I would have got 1. I would have also put xx and I would have got 1. We only want Galilean invariance, which is rotational invariance, that is all maintained. But in relativistic theory, you have another object which is this divided by 2 omega p, which is perfectly Lorentz invariant. There is no such thing for this. There is no way you can start with a d3x, multiply it by some square root of something or whatever, and obtain a relativistically invariant 4-volume description. Okay? So even at a basic level, you see that in relativistic theory, when you deal with x and p differently, even to write in completeness condition, you are going to run into. Okay? This way all taken individually might appear to be trivial issues. And in fact, if you abandon Lorentz invariance and you say that, look, I want a position operator for a particle in a given Lorentz frame. I mentioned to you there is something called Newton-Wigner position operator in relativistic theory which people try to work with. It can give you that description, but it turns out to be fairly useless. I mean, it doesn't give you anything further, so people have abandoned. Okay. So this is what is happening. Now let me come back to Stam.
So is this connected to that we can't have lower times length scales lesser than the de Broglie difference?
No, it is not that you cannot have length scale which is lower than h cross over mc. I mean, there is no de Broglie wavelength in relativistic theory. You think of it as h cross over mc as the limiting scale, which is the Compton wavelength. That is certainly true, but what actually tells you is that you can probe length scale smaller than that, but when you do that, your single particle description breaks down. Okay? Or rather, it is good to put it in a positive note. If your length scale is greater than h cross over mc, the ket x bra y will be 0 for all practical purposes. It is e to the minus m modulus of x minus y. So at scales which are bigger than the Compton wavelength, it behaves as though these are good localized particles, which is why we get away in non-relativistic. Okay. Now let us come back to Supreet's question. He was saying, look, if you think in terms of generators, this is the time transformation generator, isn't there a corresponding description? There indeed is, and we even wrote it down. What we said was that we gave another description. So let me again try to do this constructively in terms of the Jacobi action which I talked about. What we did in non-relativistic mechanics when we did Jacobi action was we said that the probability that a particle will go from one point to another with an energy E is given by a Fourier transform, which we wrote as integral 0 to infinity dt e to the I dt. Then here you have the regular propagator which we are fooling around with, still non-relativistic, x1. Okay, this we discussed at great length. This can be rewritten by taking this E inside. So what I need is, I'll take this, okay, let's write. So it is integral 0 to infinity dt x2 e to the minus I t h minus e. Okay. This is a perfectly valid description which we had in the non-relativistic theory. Non-relativistic. Okay. And what was this h? This h was p square by 2m. So let me even write that down. So I have a p square divided by 2m. This is the spatial p minus e. Now suppose you want a relativistic theory and we haven't done anything else. What would we have done? What is the most logical thing to do? I want to expand this x2 which was purely spatial to space and time. So let me write that here. So what I would have written in relativistic theory is that x2 I would have, okay, so there is an, let me do it step by step. First that x2 I am going to drop this tilde, so it becomes 4-dimensional. Then I use some e to the minus I, some time coordinate. But this time coordinate now cannot be this key because that key is already incorporated here. So there is some 5-dimensional system which we are talking about. There are 3 spatial time coordinates and 1 time coordinate here. Now we are going to think of space-time events here, and there is an internal time which we identified with the proper time of the particle. So there is a I mu here. Then I want to write a Hamiltonian here. Okay? And we found that the, okay, suppose I just naively write it down and see what happens. It's actually interesting. So this is p square. That will become minus p square for you because in, you are using a signature which is plus minus minus minus. So I would like to get this as positive. Then I have an energy E, something like that. Right? And I have an epsilon. Now I will integrate over this d mu 0 to infinity a. Okay? And remember that our correspondence was with the Jacobi action, and the Jacobi action expression, let me write it down for you. This is the length of the path times square root of 2m into e minus b. So what we did was, we are talking about free particles, so we crossed out v, and we wanted this to go into m integral dl. There is a question of sign involved which will kick us at some stage, but let us not worry about the sign for the minute. We want to get it go into minus m dl. So if I take e to be m by 2, it is taken care of. So let us take this expression and put e is equal to m by 2. Okay? Then I take a 2m outside. So I have taken the cube and this will become m square. Okay? What I need to do is that because of the sign change, flip the sign of this. The energy instead of E, I should use plus. So the moment I do that, I get an expression which is like this. And now I can rescale this d mu by mu upon 2m, which is our old constant, 2c into m constant. So I will ignore that constant. Then this becomes integral 0 to infinity d mu x2 e to the minus I mu. Mu has been rescaled by 2m. And here you will get box plus m square. Minus p square is box, or box is equal to minus p square. Okay? Let me make sure I got the signs right, because what we want to do is that you have, okay, let me do it here itself. What we are trying to do is p square would have been P naught square minus the standard P square. This will go, standard P square will go to minus del square, so this will become plus del square. This will become minus d square by dt square, again because of the I factor. So this is going to be minus box. Okay, our box would have been defined with this with positive sign, and this is what I have done. Okay, so this is fine, and if there is a sign error, you can always fix it, but let us concentrate on the conceptual part. We had this formula before, we had worked it out, okay? Except for these rescalings because of the convention in which the box is the corresponding to P square in relativistic theory, while the Hamiltonian is not P square but P square by 2m in non-relativistic theory, there is some rescalings which you have to do. Except for that, this formula, if I merely identify this quantity with a Hamiltonian or super Hamiltonian as it is called, this formula has the exact analog with this formula. Okay, this is what you should take home. Both relativistic propagator and the non-relativistic propagator has identical structure if you think of it as a energy kernel. You have in one case there is a normal time coordinate and you Fourier transform that time coordinate with respect to an energy. In the other case you have a proper time and you Fourier transform that proper time with respect to mass. Whether it is mass or mass square etc. are questions of rescaling the quantities with an overall constant. So the philosophy, so this is the answer to your question. It does work, and what you have written down here, this super Hamiltonian head is the generator of translation in the proper time. Just as you have a generator of translation in normal time here, and you sandwich it between two purely spatial eigenkets. In relativity, you can start with a generator of translation in proper time, which is this p square minus m square expression, and sandwich it between two events. After you have done that, here I would have integrated over this normal time coordinate, and there I have integrated over the proper time. So, in some sense, the mathematical structure is identical. It is only that we are very accustomed to working in purely space-time coordinates, and we want everything to be done in space-time without a proper time coming in. Okay? That is why we want to switch to the field theoretic description. Of course, there are other reasons as well. We are only doing free particles. The moment you switch on interaction, field theory turns out to be a lot better description of physics than fooling around with particles. Okay? But, okay, so structurally this is what is happening. So I wanted you to understand that the main difference between non-relativistic propagators and relativistic propagators is because of Lorentz invariance. And Lorentz invariance asks you to deal with space and time together at one go. The moment you do that, you have a description which translates properly. And then you can integrate out at proper time. Yeah, this is a very nice description. It tells you that the particles are propagating in space-time with a proper time in which it is going forward, and you integrate out at proper time in the end because you don't care about it. And the pictures which we drew yesterday, that things always go forward in proper time, but they can go forward or backward in coordinate time. It is just like saying that things always go forward in normal time, but things can go forward or backward in XYZ coordinates. Okay, that is what is happening. Okay, fine. So that is how I wanted to say about this. Now we will actually try to introduce the field and give a description which is completely in terms of the field. Okay, that is what I want to do next. To do that, I want to show that this propagator which we are after can be obtained, the same expression can be obtained in a completely different context. And using that context, since ultimately we are only interested in doing what this propagator is, you can write down all the expressions in a much nicer way. So I have to do a little bit of motivational lecture on why we want to do it in this. We had already done one thing. We have shown that if you look at the loops in space-time, it looks as though there is a half h cross omega associated with every frequency. This immediately suggests you are dealing with some kind of oscillator. This is the first point. The second point is that the loops also tells you that you cannot always start by saying that there is a particle. Because there may not be a particle and there can still be a contribution to the vacuum energy density, for example. Okay? So you want to have a situation where the particle can be either created or destroyed. And this again we mentioned even at the very first lecture. What relativity and quantum theory coming to that tells you is that the particle numbers need not be the same. Even the identity of the particle need not be the same. You start with an E plus and A minus, you annihilate it, what you get is two photons. So if you start with the Schrodinger equation for E plus and E minus, see E plus E minus annihilation can take place at very low velocity. So you can have an electron which is non-relativistic, described by a Schrodinger equation, and you can have a positron which is non-relativistic, described by a Schrodinger equation. When these two annihilate and produce the photon, you don't know what to do, because your Schrodinger equation description just breaks down. So the identity of the particle and number of particles will change. So you need to have a variable description for that. This also seems interesting to use oscillators. So I want to start with the oscillator. The only complication which can hit you in the initial stages is that normally when you do harmonic oscillators, you have a Q of P. Then you will write it in terms of A and A dagger, and this Q will be Hermitian. The oscillator which you think of classically has a Q which is real. So when you think of it as an operator, that operator will be Hermitian. Q star will be the same as Q. Now we want to deal with a system where Q is not Hermitian, and so you have a Q and a Q star. There are 2 degrees of freedom which I want to deal with simultaneously. Okay? This is not a big deal, but it takes a little bit of getting used to. So let me do it in step by step. What we will do is to start with a couple of oscillators. So suppose I have a classical system. This is quantum mechanics, in fact classical mechanics, harmonic oscillator to begin with. I will put mass to be unity. So I have a system described by 2 degrees of freedom, which I will call capital X and capital Y. So x dot square plus y dot square minus half omega square x square plus y square. Okay? So this is fine, but now I want to introduce another variable which I will call Q, which is going to be our final oscillator, which will be 1 over root 2, let us say, x plus I1. So clearly this is not real because I have taken x plus I1. But this quantity can be written as Q dot star, which is just Q dot mod square, which is just going to be this quantity, and then 1 by root 2 takes care of the half, minus omega square Q star. Okay. So this is mod Q dot square, this is mod Q square. It looks as though I am just dealing with a complex Q. But there are some subtle differences. For example, if you look at the canonical momenta, suppose I want to get the field equation, I mean the equations of motion from it. If you want to get the canonical momenta for Q, I will calculate dl by dq dot. You won't get q dot, you will get q dot star. So the canonical momenta come with a star. So when you finally go to the quantum mechanical description, the canonical momenta associated with Q will be Q dagger. Okay? So such subtleties will come about, but except for that, it is fine. The half factor also disappeared, which is because there are double the degrees of freedom, so there is a half which goes. Now, what do we do normally? Normally, we would have associated with capital X a set of creation and annihilation operators, standard commutation rules and all that, which is 1 over root 2 omega, some A e to the minus I omega t plus A dagger e to the I omega. And let me associate it with y, another set of creation and annihilation operators, which is 1 over root omega b e to the minus I omega t plus b dagger e to the I omega. X and y are independent variables, so the a and b in all combinations come in. Okay? A dagger is 1, this is the creation and annihilation operator commutation rule. Similarly, b dagger is 1. Other than that, all commutators are going to vanish. Now let us look at Q. What happens to Q? Q will turn out to be 1 over root 2, then an 1 over root 2 omega. What is it? I have to take x and add to it iy. So let me group the e to the minus I omega t and e to the plus I omega t separately. So I get a plus, just watch out for algebraic error, here it can be a complete disaster. So a plus ib e to the minus I omega t plus a dagger plus I, this plus is crucial, b dagger e to the I omega. Okay, this is what we call. So I'm going to call this operator as alpha, and this operator I would like to call instead of beta as beta dagger. That is just a notation, because when b goes to 0 and everything becomes real, I would have liked this to be alpha plus alpha dagger. So alpha will get identified with beta. So just for notation I have introduced it. So what that means is that, okay, actually I will take this root 2 factor in. So this is root 2. I think I would like to have that root 2 inside. So that Q becomes 1 upon root 2 omega. So let me write it down. Q is, this we will leave repeatedly. Q is this quantity, because they are going to work with Q. Alpha e to the minus I omega t plus beta dagger e to the I omega t. This is what we have. Where alpha and beta are given by this expression, where alpha is equal to 1 upon root 2 a plus ib, and beta is equal to 1 upon root 2. Okay, we have a definition here for beta dagger, so I have to take a dagger of that, that is a minus. Now, I want to work with Q, so first thing I need to know is the commutation rules for alphas and betas. These are independent variables. Now let us look at the commutation rules. First of all, alpha commutes with alpha is trivial. Alpha also commutes with beta. Okay, that I have to show. And I have to look at alpha, alpha dagger and beta, beta dagger. So let us do it step by step. So let us look at commutator of alpha, beta. This is going to be half with the product. So when I do the commutators here, I get a commutator A which doesn't matter. So then I get a commutator B that doesn't matter. Then B commutator A that doesn't matter. B commutator B that doesn't matter. So I get a pixel. Okay, this is because A's and B's are independent. Okay. Now let us look at alpha dagger. This will be half. I start with A commute. Okay, so A plus IB commutator A dagger minus IB dagger. This is what we want to compute. So this is going to be half. A commutator A dagger is 1. Then I get a commutator this, that doesn't matter, A and B are independent. This doesn't matter. So the crucial thing is this object. So there I have a I and a minus I. So the product will give me plus B commutator B dagger. So I get 1 plus 1. In the same way, when you work it out for beta dagger, you will get 2. So what does it mean? What it means is that in this cube, it actually in some sense captures two oscillators simultaneously. There is a alpha and a beta term. Alpha deals with its own creation and annihilation events. Beta deals with its own creation and annihilation events. Okay? And they don't talk to each other because all the in-between things are all going to commute with each other. You are with me up to this point. Okay. So I now have this cube and I wanted to look at its quantum theory. And that is not trivial because it is just made of two kinds of creation and annihilation operators. And we know the states are labeled by integers, and so I need an integer for alpha and an integer for beta. I will just denote the ground state as the 0, in which both of them has the 0 value as the eigenvalue. Okay? So let us see how it works out. And in particular, I want to look at one object which is defined by the following quantity. This is the ground state of the oscillator. I will write it down first and then I will work it out. Q of t, Q at t2, let me say, and Q dagger at t1, ground state. So this is Q at t2, this is Q dagger at t1, and there is a capital T with a bracket here. This capital T stands for what I introduced as a time ordering operator. It tells you that time flows from this end to this end. I mean, things propagate from x1 to x2, etc. like that. So if t2 is greater than t1, don't do anything. If t2 is less than t1, you flip. Okay? So the definition of this quantity is Q at t2, Q dagger at t1, 0, with the theta function on t2 minus t1, plus 0. I want to flip, so I have a Q dagger of t1, Q at t2, 0, theta of t1 minus t2. This is something which we will keep using in field theory, so it is good to spend a moment and get acquainted with it. Okay, this is a formal definition, but what you should carry in your head is that the operators inside should be ordered in time from right to left. Okay, don't do anything else. For example, don't change the dagger or anything. I mean, whatever is sitting here and this, you don't do anything if the time flow is correct. If time flow is not correct, you flip it by just moving this operator to this side. Okay? So as a result of which, inside the operators will always be time ordered, but whether you get a dagger or not dagger depends on what you started. So that it's a fairly simple object. So this is what I want to do, and I want to compute it. I want to see what it is. That we can do. So let us look at each term. So we start with theta of t2 minus t1, this one, and we want to look at this. So I have a Q dagger acting on the ground state. So Q is this. So Q dagger will have an alpha dagger and a beta. Beta is like an annihilation operator, so that is not going to contribute acting on the ground state. So you will have only alpha dagger coming. And ultimately I am going to have two Q's in all of them, so I will as well put a 2 omega here. that from the 1 over root 2 omega. So it is only the alpha term which is going to contribute, but the alpha term is going to contribute in the form of alpha dagger. That means, okay, maybe it is a good idea to write it to dagger expression here. 1 upon root 2 omega alpha dagger e to the I omega t now, because when you take a dagger that sign plate plus beta e to the minus I. Okay. So when this thing acts on the background, I am going to pick up just a e to the I omega term there. That is going to be e to the I omega t1. So that has made it into a non-particle state. So unless this thing annihilates the non-particle state, I will get 0. Okay? It is a non-particle state with an alpha kind of excitation, because it is the alpha which created it. So in this Q of T2, I should have an annihilation for alpha, which it is. So I get a e to the minus I omega t. Okay? So let us write it down together as e to the minus I omega t2 minus t1. This is what that quantity is. Then I am going to get theta of t1 minus t2 divided by 2 omega. Okay? So what will this be? Here it is Q of t which is acting. So there is a beta kind of excitation which is coming up. So that will have e to the I omega t2 coming from this term, evaluated at t2. Then I am going to have a Q dagger. This should annihilate a beta type excitation which comes from this, and it has minus I omega t1. So this is e to the I omega into t2 minus t1. Now what is this quantity? This is something which we have seen. This is just integral d3x x2 x1 of a relativistic particle e to the minus I p dot. Now this is another moment when you should stand up and cheer or clap or whatever. We got this object by doing a path integral for a relativistic particle with a e to the minus I m l as the action. Single particle going from a point x1 to x2. All that we did was to do a Fourier transform. Okay? Then we got the answer to be 1 upon 2 omega. The same theta e to the minus I omega t. Now we are claiming that quantity is equal to this. Okay? Now this is a remarkable result and nobody knows why it works. Don't believe any textbook or anybody else who says he understands it, because nobody does. You have two completely different systems because these systems cannot be more different than anything else. You have a relativistic particle with a Lagrangian which is minus mc square root 1 minus c square. I compute the path integral rigorously. Well, I didn't do it rigorously here, but I told you how to do it rigorously. And you apply a propagator. Then I do the Fourier transform. Fourier transform is trivial. I could have written the relation without that Fourier transform, which I will do in a minute. Then you get something. Then somebody else is working, he knows only quantum mechanics, poor fellow is working with harmonic oscillators. And he has a complex harmonic oscillator with some alpha and beta. And he computes the time ordered expectation value of that. And he gets the same answer. Okay? So the reason that, why is it that I will put when I say people don't understand it, what I mean is the following. There is no way you could have said without doing all this calculation that, oh yes, this has to be this. Then you understand it. Or at least say that, okay, this is the reason why this has to be this. And we don't have such an understanding. And that is a worthwhile problem for you people to think about. I mean, there is something here which is non-trivial. And we don't quite grasp it. And that might have something to do with the fundamentals of putting relativity and quantum mechanics together. But let us proceed with that in a rather mundane way by making use of this. So, this, yeah.
So, till now we hadn't time ordered any of our things.
Expressions. Well, actually we have, because we had this theta functions hanging around even in the propagator. So the theta functions are essentially time ordering, because it tells you that if something is going forward, you pick 1, and if it is going backward, you pick 2. Okay? So I need not have introduced time ordered. I could have just written this down. Right? So time ordering is just a fancy, condensed, but very useful notation for writing it in an expanded. Okay, so that by itself is not an issue. Okay, so you have this expression, and now let us reverse it. So I need more space, so okay. Here we will write x2, x1, okay, as integral over dp over 2 pi equal to 2. Let me write this in expanded form. I p dot, and again get the signs right, x1. So this goes to the other side of this quantity. Okay. Now we have to do a little bit more things. You would have already noticed that I have sneakily put a p here. That is because when you do this calculation, and I say this is same as this, when you do this, you do get this, but you get this with this omega p. Oh, I forgot to the omega p. No, that omega p is taken care of. Okay? Because the frequency has to match with the frequency of that particular oscillator. So that means for every p I need to have an oscillator. So the Q's also should have to have with them the p labels attached with it. So even though I wrote down here for simplicity with just one p and one q, you need all these things coming in. So let us do a little bit of window dressing there. We will change this definition to say that we are now going to deal with a qk, where there is an omega k and there is an alpha k, of course, and a beta k. This beta k I will write as beta minus k. That is again this notation. I mean, instead of associating an oscillator with k, I am going to associate it with minus k. It makes life much nicer later on when you have to switch a momentum variable and things like that. So you have done this. Now you expand the commutation roots to cover all the k's and p's. So when you do that, you have to say that the alpha of k, alpha dagger of p is going to be 2 pi to the power 3 derived delta function of k minus. This is the generalization of a single oscillator where I have just put 1. Okay, now I have to work with continuum and I have to work all these things out very continuously. So now let us try to do the same thing here. Suppose I had kept here a qk and a qp. Okay? And I had worked everything out. When I am taking these sandwiches, I am going to pick up a 2 pi factor, 2 pi equal to factor, and a Dirac delta function. That is, in the right hand side, I will have a Dirac delta function. Okay? So it is that quantity which I want to put into this. Then I could have had a p dot x2 and a k dot x1. So let me show what timing. I put a K here and I write this as P dot x2 minus I K dot x. This is fine because when I work this out, I'm going to get, yes, of course, I need to have an integral over both of them. So when I work them out, I'm going to pick up the, first of all, this is going to give me 1 over square root of 2 omega p and 1 over square root of 2 omega k, because the q's and p's will come with its own square roots. I can't combine the squares when k and p are different. But once I evaluate the commutator, it will give me 2 pi to the power 3 and a Dirac delta function. The moment I do a Dirac delta function, I am in business, because that 2 by 3 will kill one of the 2 by 3's. The square root of omega k and square root of omega p will combine to give me 1 upon 2 omega p. Then, because there is a Dirac delta function, I could have identified this p with this k, and I could have got it as x2 minus x2. Okay. So this is exactly this result which I first produced for in a similar context. And in order to generalize it, you want to have this oscillations per hour. Is that fine? You are clear? Okay. Now, rest is plain sailing. What you have got here is that you have this qk's and you have this qp's, and you have e to the ip x2's and there is a e to the minus ik x1. It looks very, very natural to combine. So what we will do is to say that this is equal to integral over d3t upon 2 pi the whole cube, integral over d3k upon 2 pi the whole cube, ground state expectation value of the oscillators, time ordered product, all this is as it is. I am going to take this and put it here. So I have qp at T2 e to the IP dot x2. This is the first operator. Let me put it in square bracket. Then I have another one which is qk at T1 e to the IP dot x1 with a dagger on it. So the dagger of this will give me this, and the dagger of this will give me the flip side. Okay? Now I am going to do the next sneaky thing, take the d3p inside. Okay, which I can do. And similarly take the d3k inside. Okay, if it is sorry. What else? K. Fine. Take that inside and define a new quantity. Just another operator for the moment. Phi of x as integral d3k or d3q upon 2 pi the whole cube. Okay, q is used. K 2 pi the whole cube qk of e to the I k dot x. This is just the Fourier transform of this qk of t. So that is what is here. Once I have integrated, the same thing is here. Therefore, this expression is 0 time ordered product of phi at x2, phi dagger at x1, time ordered product. Okay. So what have we done? We have introduced a set of creation and annihilation operators, which is here. I still need a few of these. Okay, so let me just wipe this up. I'll continue to write number. not be enough. Okay, let me wipe this off. I don't need this anymore. Okay. So what we have done was to introduce an operator phi at every point, every event in space-time by integral over d3k over 2 pi the whole cube e to the I k dot x then the qk of t, this is a good time to expand it out. It is 1 over square root of 2 omega k qk is here, that's why I didn't keep this. And we will follow the traditional way of writing it. Instead of alpha and beta, I will call it A n. AK e to the I e to the minus I omega kt plus B minus k dagger e to the I omega kt. Okay, I didn't originally introduce A because I wanted to reserve A for x and y, but now it doesn't matter. They're only going to deal with q. So AK and BK is what we have called alpha and beta. So you have this. Now let us combine these together. So you get integral d3k upon 2 pi the whole cube 1 over root 2 omega k. This is nice, k dot x and a minus I omega t. So I can write that quantity as ak e to the minus ikx. Right? Now standard notation. But if I look at the other quantity, I need to again play a trick because that quantity has a e to the I omega t and e to the I k dot x. I would like this to come with minus signs. So in that term I am going to change k to minus k. This is why with great foresight and wisdom I put a minus k there. So now the notation looks easier and it becomes bk dagger e to the I k. Okay. So we again need to take stock of the situation because a lot has happened and we need to understand what has been achieved. We said that we want to represent this in a different way, which will hopefully give us an evolution in a rather causal manner from one time t is equal to t1 to another time t is equal to t2 without any proper time and super Hamiltonians and all that coming. So then we said that taking a q from this half h cross omega, maybe we should look at oscillators. So we introduced an oscillator, which was a complex oscillator, which had a creation and annihilation operators, two sets of them. Then we had the ground state of this oscillator. Then we found that when you compute the expectation value, the ground state expectation value of the time-ordered product of this q and q dagger, you got back the Fourier transform of x to x. That gave us a q, so we did the inverse Fourier transform. And in the inverse Fourier transform, we found that there is a natural combination qt in e to the I p dot x coming up. So you took advantage of that and defined this entire combination as phi. Even at this stage, you have no clue of any Lorentz invariance. Okay, it's a three-dimensional Fourier representation of some qk of t. Then you plugged in the exact form of that, and then it had a e to the minus I omega t and e to the plus I omega t, and you combined all of them and you got it. We are almost there, and we want everything to be Lorentz invariant. In order for everything to be Lorentz invariant, this should be 2 omega k, not square root of 2 omega. But that is easy to get. instead of AK, introduce a set of variables capital AK, okay, which is small AK. Capital AK should turn out. I want to put capital AK here, which should have this root omega k. So what I'm going to do is that I'm going to write this capital AK divided by root 2 omega k to be equal to the lowercase a. So the lowercase ak I will replace by capital AK divided by root 2 omega k, so everything will be fine. But why is this required? There is a reason why this is required. I wrote down a computation rule for AK. I said AK, AP diagram was 2 pi t whole cube derived as a function of k minus p. It should have alerted you there that these AKs are not fully Lorentz invariant object because the right hand side is not Lorentz invariant. We saw it in the previous lecture that for Lorentz invariant there is a 2 omega k is required. So if you look at the computation rules between AK and AP, it's just a scale. AK and AP would be square root of parameter. So that would have been 2 pi equal to 2 omega p or omega k, direct k. So what we have shown is that I could have written the same thing as some A of x plus b dagger of x, where just like this field, A of x is integral d3k. I'm going to use one more notation, d omega k ak e to the minus ik. What is this notation? This is just the invariant element in momentum space. I'm kind of writing it down as d3k upon 2 pi whole cube and 1 over 2 omega. Okay? So there between the invariant, Lorentz invariant momentum integration element with the 2 pi thrown in, I am going to call it d omega. So this AK, if I replace it by this capital AK upon 2 omega k, there is going to be an AK e to the minus ikx and this next thing. This is the manifestly Lorentz invariant part. Similarly, I have a b of x, which is integral d omega k bk e to the minus ikx. Both of them go with e to the minus ikx, but here the field is defined as a plus b dash. Alright? And your a's and b's are Lorentz and obey a Lorentz invariant computation. So this is again remarkable. Just think about it. We started with harmonic oscillators. Harmonic oscillators know absolutely nothing about Lorentz invariance. Then we computed the vacuum expectation value of the time-honored product of two harmonic oscillators. Sure, harmonic oscillators go as e to the minus I omega t. Then there is a e to the ip dot x when you do the inverse transformation. So that part is not probably too surprising that you get e to the minus ikx and e to the plus ikx. That is fine. We even put a minus b so that it will work out and out. But what about the overall factor? The overall factor is 1 over root 2 omega arises in quantum mechanical harmonic. You have studied that. You have studied this expansion in quantum mechanics. Nobody ever mentioned anything about Lorentz invariance at that time. But that 1 over root 2 omega combines with another root 2 omega to give you precisely the factor which you need, where when you do this integral, you get a Lorentz invariant result. Okay? So all these things ties in very nicely. The only place where we threw in Lorentz invariant in the oscillator is in saying omega k is square root of k square plus m square. That of course is a Lorentz invariant dispersion relation, but nowhere have we used that. I mean, that is hiding inside this in order to maintain Lorentz invariant, but the prefactors is what I am talking about. So there is a lot of remarkable things which happen in order to tie it up. The reason I am saying this is that when you actually go into field theory with these oscillators, you are going to get huge number of counterintuitive results. Lots of things which has to be finite will become infinite. We will have to fool around with various things, etc. And you can very easily lose faith. I mean, are we doing something totally wrong? But the fact that a lot of these things gel quite nicely should tell you that we are not doing anything wrong, and that is the way it should be interpreted. Okay. So we have gone up to this, and this is the first time, and these are the things which are called incidentally fields. That is what the course is all about. But right now, these are just some operators which I have constructed out of harmonic oscillators. Okay? So these are just operators sitting at every event in space. And then when I go and compute, this quantity, I end up getting it. So now I have a completely different alternate interpretation of what the propagator is all about. The amplitude for a relativistic particle to go from x1 to x2 can be thought of as expectation value of a time model operator. So if we understand this, maybe we will understand this. And in order to understand this, we have to ask, what is it acting on? It is acting on some space of harmonic oscillator energy state, eigenstate. I mean, this is the ground state of the harmonic oscillator. And we don't even know what these oscillators are yet, which we have to identify, and all that we will do in good time. But I want to now come back and look at this Lagrangian. See, we wrote down this Lagrangian here. So we want to know what that Lagrangian means in terms of this field which we have written. Okay? So let us do that. That is easy, and we can probably stop with that. So if I look at this Lagrangian is nothing but q dot square, complex square now, omega square mod q square. This is essentially going to be, so this is the Lagrangian. So if I look at the action, this will have an integral over dt of this L. Now, of course, you can write this q in terms of phi. That is just an inverse Fourier transform. So q dot will be phi dot e to the I k dot x. So if I take q dot square and integrate over some quantity, you are going to end up getting integrals over phi dot, except for one complication. This is still two oscillators. We want one oscillator for every k, which I have not thrown in yet. So I have to put in first a k label here, and a k label here, and a k label here, and I have to take all the oscillators together. So I have to sum over all the oscillators. So here is the Lagrangian for Lk and sum over. But that summation is going to be an integration. So in the continuum limit. So now we have got a straight beam which has an integration over time and an integration over some Fourier variable. d3k upon 2 pi the whole cube times mod qk dot square minus omega k square qk square. This is what we have. Okay. But then there is some theorem, I think it is usually called Parseval's theorem, which tells you that if I take q dot square k and I do an integral over all d3k, that is the same as taking its Fourier transform, doing the dot, taking the square of that and integrating over all else. Same goes for this. But in this, we want to do it in a slightly different way. In fact, we have to do it in a slightly different way. Because there is a k lurking inside this when we are doing the integral. So I have to separate that out. So I have to write this as minus m square mod qk square then I get a minus k square mod q k square. Here is where we are using the dispersion relation. Omega k square is separated into these two terms, right? This minus omega square becomes this. This is posing no problem because this can be obtained from a mod phi square. Okay? But this, you have to be a little bit careful because there is a k square here. But that is not an issue because I can take a gradient of the phi. So what am I doing? What I am going to do is to use that relation to write down whole lot of things for qk in terms of phi. Let me do that for you explicitly. So first I have qk of t, which is integral over d3x of phi t comma x. This is this with an inverse transformation e to the minus I k dot x. This tells you immediately that qk dot, which we need there, is nothing but d3x phi dot of t comma x e to the minus I k dot x. What we need is that k qk. For that, what you do is that you do a gradient. So if I had a I k qk, okay, Ik can be obtained by taking a gradient of this, or rather minus Ik qk can be obtained by taking a gradient of that. So that is d3x del phi e to the minus Ik dot x. What has been done is that you are taking a gradient and then you are flipping the del to this by taking a total derivative which you are told. But essentially you are saying gradient of phi will give you a k in the k space, and that is what you are using. So each one of them has a corresponding Fourier transform in terms of this. We only have to plug it in. Okay. Again, you guys work out the signs and things like that. So all the d3k integrals are now going to become d3x integrals. So you will have integral over dt. You will have an integral over d3x. And you will end up getting phi dot mod square. This integration is going to become phi dot square. Then you will pick up a minus m square mod phi square. That is going to come from this. Then this is going to give me a gradient. Right? This is very nice again, because this can be now written as integral d4x dt and dx nicely transforms, combines together in a Lorentz invariant way. This also nicely combines in a Lorentz invariant way. So what you have got here is dA of phi star minus m square phi phi star. So the system which we started with, which was a bunch of harmonic oscillators, was actually Lorentz invariant. Okay. The moment here, of course, this goes in very, very crucial.
Sir? Yeah, about this thing only.
Yeah.
Is there a way to motivate this dispersion relation? You have put in this omega k square as.
In this particular case, we want to identify that e to the minus I omega k. Right? Therefore, you originally see, our whole motivation of doing any harmonic oscillator was that x2, x1 propagator should be expressible in terms of the oscillators. The x2, x1 propagator has a e to the minus I omega kt, where that omega k is square root of k square plus m square. Therefore, it is already keyed in. What I was about to say was that starting with a bunch of harmonic oscillators and A's and A dagger, with some omega of k, which need not be this, and introducing their ground state, their excited states, etc. is a very standard practice in condensed matter physics. So suppose you are talking about lattice vibrations and you want to create and destroy phonons. This is exactly what you will do. Your ground state is a huge solid with some 10 to the 24 atoms. So it is not a vacuum state by anybody's imagination, but it is a vacuum state for the phonons if there are no lattice vibration. Then you create one phonon, two phonons, three phonons, and then you have interactions, etc. Then the phonon dispersion relation is what will go in here, which of course will not have Lorentz equations. But here we are thinking of something like a space-time lattice. We don't know what it is. The excitations of that is what appears as these fields, and the ground state is all these oscillators, which is lying dormant. And when you excite it to a one particle state, and that particle has an omega k as the energy and k as the momentum, and they satisfy the relativistic dispersion relation. Okay, we will be exploring it in great detail as we go along. But the main point I want to stress is that again magically you find that the system which we dealt with maps to this. Now this is nice because I had the harmonic oscillators thrown in, but now I can take the harmonic oscillators off. I can work entirely with this file. Remember that the x2, x1 which we were after, just answer, x2, x1 which we were after was this quantity, phi at x2, phi dagger at x1, 0. So if I know the dynamics of phi, I am through. Okay? I obtained this expression from oscillators, but since they have served their purpose, I can throw them away. And the dynamics of phi can be obtained from this Lagrangian. So I have a Lagrangian for some set of operators phi, the corresponding Hamiltonian, and if I can study the dynamics of that and decompose them into oscillators in order to identify this ground state, then I can get this from this. Yeah, there was a question? Yeah.
So then LK, we are summing over K's. So
Yeah.
LK be there in the Lagrangian.
This, oh, okay. So what I meant was there is a k here also. That is, you take the Lagrangian for each k, sum over all of them, then integrate over t. Okay? There is a whole bunch of harmonic oscillators, infinite number of them, labeled by k. Now, incidentally, this should also tell you why I had to deal with, I dealt with a complex scalar field here, because the phi and phi star are not the same. You might have thought, and this is worth looking at because some textbooks make a mistake here. I mean, purely typographically, but none of the results are wrong. Suppose phi was real. There seems to be a feeling that if phi is real, you can deal with a q which is real. That is not true. Because if you take this and take a complex conjugate of that, you will immediately find that q star of k is q of minus k. So q star of k is not q of k. So q is not going to become real just because phi is real. So the oscillators which you have to deal with, you are sum. You have to deal with complex oscillators. There is no way of getting out of it. But if phi is real, certain things simplify, and if phi is complex, it is slightly more complications arise. But I want to keep phi complex for a very important reason. In the next lecture, we will try to interpret this in terms of particles and antiparticles. Things get enormously confusing if phi is real. Because if phi is real, it turns out that the particle is same as the antiparticle. So as a result of it, you don't really know whether you are talking about particles or you are talking about antiparticles. So I want to keep phi and phi star as distinct, so that the particle and antiparticle are distinct until you are familiar with what is going on in the propagator in terms of this, and then we can study a real scalar field. Okay, I think that is a good place to stop. So we have come obtained up to this. Now the rest of the thing, which I'll probably take up tomorrow, is to interpret this. And that is very, very important because it is connected with the concept of causality. Just to remind you what is going to come, remember that one major problem, so to speak, which we found with the propagator is that if I take the space and time and you start with this point 0 and you ask what is the amplitude for the particle to go from here to here, which is outside the light cone, that was nonsense. Of course, small e to the minus im times Compton wavelength suppression and all that, but nonsense. Then we said, oh, what about causality? Then I said there is no problem with causality because I would have done this. Okay, this particle was propagating within the light cone, this was propagating within the light cone, this was propagating within the light cone, and I am thinking of a pair creation event here which got annihilated with this, and everything is within the light cone and I can describe. The only problem was I needed to have a description which will handle multiple number of particles. Now that we have got a field which is supposed to take care of infinite number of degrees of freedom system, there must be a way of interpreting these kinds of propagations in terms of this. Okay. And also to show that there is a nice way of thinking of causality. There is something which should vanish outside the light cone. Okay, this propagate is not vanishing, but there should be something else which vanishes outside the light cone. We will identify that. And that is what is going to tell us why we need two fields rather than one. Just think about this. There is one field here and another field here. And we took our phi to be A plus B diagonal. Couldn't we have done with just A or B? We couldn't have. Okay? That we will show. Questions?
Phi being real shouldn't be a problem for photons.
Okay. First of all, photons are not scalar. It's a vector. And in that case, photon is its own antiparticle. And in fact, most of the time when a tube light emits photons, it emits antiphotons. Okay, because okay, in fact, that is probably a good time to mention this. See, when we look at the solutions to a Klein-Gordon equation or some such thing, you have e to the minus I omega t and e to the plus of omega t. Then the textbooks will go into a panic mode and say there are negative energy solutions, this is very dangerous and we don't want to do this, etc. Then there will be another chapter in the same textbook where they will deal with Maxwell's equation. They will have a box A mu equals 0. They will solve that. They will have e to the minus I omega t and e to the plus I omega t. Okay? You never think in terms of negative energy solutions for photons. They have been there all along. I mean, every electrodynamics course, you have been dealing with e to the minus I omega t and e to the plus I omega t without ever saying photons have negative energy. That is for the same reason that photons are their own antiparticles. So as a result of it, this distinction just goes away. So whenever you deal with systems which are their own antiparticles, it is considered to be extremely confusing in the initial stages. So we will keep them distinct, understand what is going on, and then we will deal with photons much later in the course.
We first started with 2 degrees of freedom.
Yes.
Yes. We are incorporating the infinite degrees of freedom by
Yes.
summing our field.
That's right. So the reason I started with 2 degrees of freedom is because I wanted a complex oscillator. A complex oscillator is equivalent to 2 real oscillators. Yeah.
Sir, as we say, phi and phi diagram are particle and antiparticle, and in
What are particle and antiparticle?
one represents particle and one represents antiparticle.
No, that is not true. That is the whole point. It is not that phi is a particle and phi diagram is an antiparticle. If at all you want to think in terms of that, A is a particle and B is an antiparticle.
Yeah. What I want to ask is, when we use time reversal operator,
Yes.
then we use complex contributor there.
Right.
And in last time when we say what to take out, minus x r n,
Right.
and then this, and
I said only the phase
yes,
changes.
yes.
Yeah.
And Euclidean time or imaginary time gives correct answers. Is that has some relation with this?
You are asking, is there a relation between time reversal giving you complex conjugation and Euclidean time giving the correct result?
Yes.
No, not in any simple-minded way. See, the Euclidean giving the correct result, I explained to you even in the earlier thing that it's again a deep mystery. Most of the time, people started with the Euclidean extension as a mathematical trick. But you cannot but admit that there are things in quantum field theory which makes a lot of sense in the Euclidean sector, like the Euclidean action and things like that, which can all be translated into real time. But then it looks much more horrible. Okay? So there are certain things which Euclidean time brings in, which is very nice. I told you about the periodicity in imaginary terms giving you a temperature, and these features you don't know how to translate into real time. But that is a mathematical issue. In the Euclidean time, you have done away with this I in the complex space. So the time reversal operation does not have a symbol interpretation. Okay. Now it is also related to the group structure, because when you start with a Lorentz group, there is a signature which is -1 and plus, and when you change that I and you think of it as a rotation group in 4 dimension O4, it has a different structure. Okay, so it is more like reversing the space and reversing the time has no distinction in that kind of a context. So I don't know of a simple connection between these two. But coming back to your original point, do not think of phi as particle and phi dagger as antiparticle. We will spend time and sort that out. If at all you want A is a particle and B is an antiparticle, and phi is A plus B dagger. So it is very important that your field operator captures the dynamics of both particle and antiparticle simultaneously. If it does not happen, causality will go for a toss. So we will spend time for it. Yeah.
So this correspondence between infinite number of harmonic oscillators and a relativistic particle, for that we actually calculated first the propagator for a free particle, x to x.
Right.
Then we calculated the expectation value of the time order
Okay.
for harmonic oscillators. Now suppose, and for calculating x to x, when we started with the Jacobi action, and there we used some tricks to evaluate.
Yeah, or you could have done it on a lattice more rigorously. Yeah.
So now suppose you have a relativistic particle given potential.
Yes.
And correspondingly, if you take this infinite number of harmonic oscillators and put that also in a potential, then do this correspondence hold?
No. For several reasons, no. First reason is that there is no such thing as a relativistic particle in a potential. You cannot even write down a Lagrangian for a relativistic particle in an arbitrary potential, because it will not be Lorentz invariant. Lorentz invariance puts a very strong constraint on what kind of potentials you can put a particle in. It can be a vector, it can be a second rank symmetric tensor, if I am thinking in terms of integer space. There it stops. Okay. So this vector happens to be electromagnetism and second rank symmetric tensor happens to be gravity, and nature has exhausted all the possibilities. Now you can go, and gravity we don't understand, so we will not talk about it. So if you take electromagnetism, it turns out that if you have a spinless particle in an electromagnetic field, you write down the Lagrangian, which is half x mu dot, and then you put a mu x mu dot. There is a way of doing the whole thing in terms of particle trajectories. It's complicated, but it can be handled. But if there is spin, or if there is some other field, then we do not know how to do that. So the harmonic oscillators do not get deposited in that potential. The harmonic oscillators get modified. You get a new set of harmonic oscillators. I mean interacting harmonic oscillators. There will be coupling between the oscillators. So the moment you have interaction, all these cases here, these are independent harmonic oscillators. I forgot to stress that, but it is obvious from the Lagrangian. These are not interacting with each other. The moment you switch on the interaction, these oscillators couple to each other. That is what happens. So it is not like a harmonic oscillator in an external potential gives you a relativistic. I mean, a harmonic oscillator